Okay. Video. Now there's no record of any of this nonsense. um, so what do you all see when you look over here? Do you see like a big me and then like a bunch of people? That's kind of what I see. You guys can hear me?
Yeah, just it doesn't look big. It's just you and a bunch of names. You're not huge or
Okay.
anything.
Got it. Got it. Okay. Alrighty. So I should probably do something like, let's see here. Okay. Oops. Okay. All right. I'm going to share a screen here. I'm going to try that one. Oh, I can do multiple windows. Cool. Let me try this. This is actually okay, right? It's not like, it could be like more loud and like clearer, but like I feel a little bit more comfortable when I can sort of navigate using this stupid side tab. Is this okay? Yeah, it's okay. What am I doing? What
Yeah,
am I saying?
it's good.
It's all right. It's all right. Good morning, Cindy. How are you?
Good morning.
Uh, oh goodness. Let's see. I'm trying to get this thing sort of more or less. Oh well, I give up. Nice stupid computers. Okay, so so we did this one last time. Now, part of the problem with doing absorption is that the cuvette has interactions with light that don't have to do with the analytes absorbing. You know, this is actually instrumental analysis at its sort of boring best. But so you know how we did this whole deal where we showed you, using calculus and everything, how the absorption was related to concentration. A equals epsilon BC. Well, there are other interactions that light has with the cuvette, right? If we sort of zoom in on this guy here. Oops. Oh no, that wasn't right. Oh man, here we are. I don't even know how to do it, but you can see uh, there's the incident light P0, and then it hits this wall, and then it retro reflects, right? Well, that's just that happens, and this is maybe a few percent actually. Depends on the difference in refractive index between the air and the cuvette, right? And there's a formula for that. It's called Snell's law, and at any given interface. Oops. Oh geez. Oh man, my computer's thrashing. Anyway, we'll see. It's the reflection. Uh, it's n1 over n2 squared that whole thing. And then there's an angle dependence. I can't quite remember that one now, so forgive me for one sec there. But so you can see that every time the light encounters, even at normal incidence, an interface, there's a reflection, right? And so what we're showing you here is actually just the first order reflection, right? It's like when the light comes in and it hits this wall, right? It reflects back, right? Then most of it's transmitted, then some of it hits this wall and it's reflected back, right? But then this light hits this wall and it's reflected back, you know? And this becomes like a little bit of a cavity, right? And then this becomes a cavity and this becomes a cavity, you know? But so you don't have to analyze it all sort of separately. We just correct for it, right? And it's called a baseline in this jargon, right? So the baseline absorption there is the absorption due to everything except the analyte. Okay. Now let me ask a question here. What is N1? What are N1 and N2? There's N1 and N2.
Is it the coefficient, Dr. Tim?
Or indices of refraction?
Yes, it's the index of refraction of, for example, air and glass. You know, that'd be this first reflection here, right? And then glass and solution, right? And then solution and glass, and then glass and air, right? So let's say that we do our very best, right? And we have an aqueous solution, right? And you have two solutions. You have an aqueous solution and an aqueous solution with analyte. So you have a blank and an analyte, right? And in that case, there's really three N values to be concerned with, right? There's air, glass, and then the refractive index of the solution in here, right? Or actually, maybe you could say there's four, right? And I'm just going to list them down here. Let's say there's N1 is air, N2 is glass or quartz, and 3 is the blank solution, and 4 is the sample solution. Okay. So so when you change from blank to sample, right, does the air refractive index change? Just for giggles? No, right? How about the glass? Does the glass refractive index change? No, exactly. Okay, so now when you change from blank to sample, does the blank solution refractive index change when you switch to sample solution? And the answer is, oops, I'm going to put you somewhere where I can see you here. There we go. And the answer is sorta, right? Now, it's possible to have a very good match between sample and reference in terms of the refractive index. It's possible to have a match that's so good that you never see it in practice, right? But that requires that some things stay the same between the blank solution and the sample solution, right? So let's see here. Let me put it in here. This requires, oops. Okay, I'm going to try to make it a little bit bigger here. Oh, come on now. Stop snaking around. This requires that N3 equal N4, right? Which in turn means that the bulk of the solution is the same. Like the same solvent, right? So you wouldn't want to go from water to methanol or methanol to acetonitrile or something like that, right? So water, right? That's good. And then the other major components, right? So ionic strength. Etc. Right? So if you're measuring, let's say you have, let's say you're measuring the absorption of dye in Kool-Aid, right? I know it sounds pretty cheesy, but it's something that I'm sure somebody has done, right? Yeah, excellent.
Chem 1A.
Oh, excellent. I love it. I love it. So, oh no, but in Chem 1A, you probably didn't make the proper corrections. Oh no.
We subtracted the blank, but yeah.
Probably you just use water as your blank, right?
Trying to remember, probably.
Yeah, probably just water.
I mean, it would have been the same deionized water we used to make the Kool-Aid, but yeah.
Right. So now the absorbing parts of the Kool-Aid are only the colored ones, right? But if the Kool-Aid has any sugar in it, right?
Oh yeah.
Right. The sugar will have a fairly substantial impact on the refractive index. It tends to raise it. So in order to make the absorption measurement accurate, you have to raise the refractive index of the solution on average to that of raise the blank refractive index of the solution on average to meet that of the sample, right? So you need to add sugar because sugar, so it brings up an interesting question, like, does sugar have a visible absorption, right? Does sugar water have a visible absorption? Somebody other than Cindy answer this. It can be someone smart, I don't care. Casey?
It's too early to process any of those.
Oh my God. I did not sleep a friggin' wink last night. First of all, I ate a stupid Beyond Burger last night, which sat in my stomach like a Beyond bomb. And I just did not sleep at all. But my brain is processing, man. It has to process.
Wait, what was the question, Dr. Taro?
The question is, does a sugar solution absorb visible light?
No.
It does not, right? But does a sugar solution have a refractive index that's different than water?
Yes.
Yes.
It does. Absolutely it does, right? You know how you can tell that is when you stir the sugar into water, you can see Schlieren lines, right? Schlieren lines are they're not really lines. They're just they're variations in refractive index that make wavy kind of features in the water, right? Same thing as like when like when you see a lake in the desert or something, that's just the low refractive index air heating on the surface, and the light can reflect off of that. And so these are all cases where like there are differences in refractive index, but not necessarily differences in absorption, right? And now I have to bite my tongue a little bit when I say that, because really one implies the other. There's a causal relationship between absorption and refraction, and it's a really interesting field of study, and that's called there were two physicists around the turn of the 20th century. One was called Kramers, and he was American, and Kronig was like Dutch, I think. And so they together they developed a relationship called the Kramers-Kronig relationship, and that actually it sums everything into a complex number that is the real refractive index. So we're even though we're taking this to another level of detail here, we're still sweeping the second level of detail under the rug. And it's generally absolutely fine, because unless you have very strong absorbers, the Kramers-Kronig type oscillation in refractive index is not important. So I just gave you a long, probably fairly opaque introduction to the Kramers-Kronig relationship and other stuff like, and why we don't use it actually.
Opaque introduction.
A vague introduction, thank you. So,
No, it was a pun, Dr. Terrell. You said opaque.
I love it. So what is this crapola here? I just say add slide, and it's like all this shit. Okay, so so there's oops, come on, dude. Snell's law. And maybe Fresnel's, which says, basically that the blank and the sample should have the same refractive index. And if we want to be absolutely clear about it, we're talking about the real part, not the complex part. But don't worry about that. Right? And then so chemically this means, oops, let me make this, I just don't get it here. Chemically what this means is that we're talking the same concentrations of non-absorbing species. Which are at appreciable concentrations. Right, so let's see. Oh God, thanks. So this is going to be how to make a blank. So from the fundamental perspective, we need the same refractive index in the two solutions. And that means the same concentrations of the non-absorbing species, which are at appreciable concentrations. So as an example, right, if you have, say, a millimolar salt concentration, 10 to the minus 3 molar, or something like that, then it should have maybe 10 to the minus 4 change in refractive index, 10 to the minus 4, 10 to the minus 5, something like that, right? So like e.g., 10 to the minus, so let's say 0.001 molar, say sodium chloride, might give you a change in N of, say, plus 0.000001, something like that, yeah? 10 to the minus 5 or 6, actually, 5 there, right? But that's not really measurable. Right? If you had a 1 molar sodium chloride concentration, you would absolutely have to match that, right? And if this is part of your matrix, right, then you have to match it. In the blank. Yeah. Excellent. Any questions on this? Good, good, good. Okay, so now another thing is, you have to have the cuvette be the same, right? And there's different types of cuvettes. Yay, big deal. And then the positioning of the cuvettes is important, right? And, this is probably fairly accurate here. This diagram, which says relative standard deviation in percent versus absorbance, right? And it's kind of interesting here, right? Because, and even just ignoring the difference between the old cuvette holder and the new cuvette holder, right? This relative standard deviation gets up around 100% when the absorbance is around 0. And let me ask you a couple of things, right? First of all, is a large relative standard deviation good or bad?
You can argue it's good because it means everything is going to fall within one standard deviation.
Oh.
I don't think that's the answer you were looking for.
All right. All right. So somebody else turn your camera on, please. Casey has volunteered. Casey and her guitars.
I don't play those guitars. I would say it's bad.
Okay, you would say it's bad. Jonathan, what would you say? Hey, Kareem. Hey, Vin.
I'd say it's generally bad.
Yes, a large standard deviation is bad. Exactly. Yeah, Fan? Is
Yeah,
it?
I'm in my car.
Oh my gosh. Are you coming to lab today?
No, yeah, I have another lab after this.
Oh my gosh. Okay, well, welcome. Yeah. So a large standard deviation is bad, right? And what this is talking about is the standard deviation and the absorption that you measure when you take the cuvette out and put it back, right? You just leave the stupid instrument on, you take it out, put it up, take it out, put it back, take it out, put it back, right? And when it's in place, you measure the absorbance, right? And then between placings, you get a different value, right? And the relative standard deviation in that might be pretty small, but it's not a zero, right? So now I would argue that it's definitely possible to get larger than 100% standard deviation when the concentration is really zero, right? Or when the absorbance is really zero. Because zero, if it actually is zero, then any value other than zero will give you an infinite, change, right? Because it's one minus the other over zero, right? Times 100. So that's why this left side of the graph that's why it's a maximum around zero absorbance. Does that make sense, Kareem? Excellent, good answer.
Yes.
Excellent, cool. Actually, I think you actually understand it too, because you have a smile on your face that indicates, okay, I kind of understand this. Casey is still evaluating something other than chemistry. It's probably coffee.
Tea.
Tea. Okay, good. That's very.
And I understand it.
Okay, good. Excellent. How are you doing, folk? Okay, cool. So now, you think you get it? Okay, cool. So now, how would we measure, for example, this point right here? Absorbance of 1.5. So that means we've got a solution. We blank corrected, and the solution has an absorbance of 1.5, right? And we take it out and we put it back and we measure it again. And under those conditions, the relative standard deviation is about what percentage here? Can you read off this axis?
Really,
0.05.
really small.
Oh, yeah, small.
Yeah, exactly. About 0.05%, right? So that's pretty small, right? So that's pretty good, right? With the old one, it was like 0.1%, but it's really not a huge amount. It depends on what you're trying to measure, right? So, so this is just, I don't know, it's an interesting example of what an analytical chemist whose answer depended on an absolute absorption might have to worry about, right? So if you were to continue this out to higher absorbance, what would happen? If you went beyond absorbance of 2, what would happen to the relative standard deviation in the absorbance value that you measured?
At 2 or 0.2?
No. Absorbance of, if you took all these points, right, and you said, why did you stop at 2? Let's go to 3, right? Let's take
How
this.
much light is actually going to hit our detector, though? Are we going to be able to measure that?
Right. So it will be more challenging from a detection perspective, right? Right. And so will the standard deviation go up or go down? It will go up. Exactly right. It will go up. So
Well, I mean, based on the graph, it looks like it is sort of starting to go back up.
Yes, it is. Exactly.
Is that
Exactly right. That's exactly right. Yep. Yep. So uh so it goes up because the light is going down. And what if the absorbance is 2, what is the transmittance?
two minus log 2
Uh
or 1 minus log 2? Sorry, I'm just guessing. Somebody else can answer.
I'm thinking, I don't know. I don't know when you put it like that. I think it's the transmittance. The way I do it, I can do transmittance on even values, right? When the absorbance is 0, the transmittance is 1. Absorbance is 0, transmittance is 1. Absorbance of 1, transmittance is 0.1, right? So this is transmittance of 1 here at 0 absorbance, right? That means P and P0 are the same. You go to an absorbance of 1, and the transmittance is now it's 10% or 0.1. Then you go all the way out to 2, and now the transmittance is 1% or 0.01, right? And then as you go out to 3, it'll be 0.001 or 0.1%. And that's where things start to get dicey, right? It's hard to measure as the light goes down and down, right? And there's actually a bunch of reasons for that. There's one very fundamental reason, is that the amount of noise in any light beam in the, the amount of noise in any light beam is proportional to the square root of the number of photons in the beam. Because, when you break it down, light is discrete particles, right? And there's no such thing as a beam that produces the exact same number of particles. Like it produces one photons like that. The photons, they come distributed with a certain distribution. And there's a distribution of the distance of the time interval between photons. And that means that you get that contributes a certain amount of noise to the photon count. And so for an intense beam, like an intense blank beam, there's actually, let's say it's 10,000, right? Photons per second, right? Then the amount of noise is 100 photons per second. And so if your absorbance signal then is at 2, right? So you're absorbing 99% of the light, then your signal to noise ratio is 1. The noise is 100 and the signal is 100 photons per second. So
Terrible.
That's terrible, exactly. Exactly. Now, and it'll get better if you add more light. But but it will get worse if you add more light to the blank but not to the sample. Right? So anyway, I think I've kind of beaten this horse to death, but these are fundamental limitations using the counting statistics of light that pop up. And it made me think a little bit about the quantum of light, and they're what they call single photon sources of light now. And it's basically where you have a single entity that creates the photons. Maybe it could be it could be a single nitrogen vacancy in a nanodiamond, yeah, and that's pretty robust. They're because they're in a diamond, they're protected and they can create many photons, right? And the counting statistics for those might be different, you know. It could be better, but you know, still, it's before we ever make a measurement with that, we'll have to think about that. Okay, so, and it's not going to be in any instrumental analysis course for many years. Okay, so position the cuvette reproducibly. Yeah, good. So, oh God, this is so complex. Okay. So these are practical different ways that you can measure absorption, right? And so if you have a non-absorbing solvent, right, and the analyte absorbs at 278 nanometers, right, you can just measure at that wavelength and that'll give you the absorbance, right? Yay. No, there's no mystery there. That's number one. Number two is that if your analyte does not absorb, but you can add something that will make it absorb, then you can do that. So this will be this would be called a chromogen.
Is that like that homework problem where we added the thing to the iron to make it red?
Exactly. Chromogen, e.g. SCN minus to iron 3, right? Or the other one, which was NH3, and then to make that that blue thing. I forget what it's called now. I'm just going to erase that. I don't remember. I have an example. Okay. So then if you have a mixture of analytes, right? And they have overlapping but distinct spectra, then if you measure at multiple wavelengths, you can sort out how much of each is in there. So this is something we'll deal with in the next chapter, right? And then also you can chemically separate things, right? So, you know, you can put them on a column, separate them, and then remeasure them, right? That's always possible. Well, sometimes possible. Okay, so so here's an example with hexane, you know, and it's not really so complicated here, right? It's just A equals epsilon BC, right? And so you can calculate the molar concentration of benzene, right? And then epsilon equals A over BC. There's A, B is 1, C is 1.32, you know, and that gives you 201 per molar per centimeter. You know, it's not really so difficult, you know. And then if you have a different path length, and so knowing the extinction coefficient, right? If you know the extinction coefficient, right, this guy right here, then you can calculate the concentration of benzene in whatever solution you have, right? So here, you take the absorption that you measure, divide by epsilon and the path length, and that'll give you the molar concentration, right? So here's an interesting point, and this is actually directly relevant to the first lab, which is if absorbance is 0.07, is the absorbance going to be an accurate value? I mean, is there anything inherently bad about an absorbance of 0.07? I don't think so. I don't think so. So an absorbance of 0 would be bad, obviously, right? Because you can't measure anything. An absorbance of 10 would be bad because it's not really even an absorbance. It's just a lie that your spectrometer is telling you. An absorbance of 3, to what transmittance would an absorbance of 3 correspond? So here's a hint, Casey. If absorbance is 3, transmittance is 10 to the minus 3.
Yeah, I was trying to think of your chart. I remember we did that on like one of the first days. And like it was like 0.0001.
Exactly.
Like really small.
Exactly. Cool. So so those are, so you have to avoid the extremes, right? The 0.07 is fine. And so long as the absorbance is in range, then you can do things like this. So now if the absorbance here were 7, right? Like the instrument were giving us like, no, it's too much, right? Then what could we change very conveniently in this experiment to get the absorbance down to say 0.7? So going down in absorbance is actually fairly easy to do. And there's a couple ways you can do it.
Dilute the sample.
You can dilute the sample, exactly. That's one way. That's the easiest answer. There's also another fairly simple way to do this. And if for example, here we have a 5 centimeter path length, that's a pretty weird cuvette, right?
It's like, yeah, can we change our cuvette?
Yes, exactly. We just go to a thinner cuvette, right? And we measure blanket sample with that new cuvette. And so going down in absorbance is not that hard usually. Either dilute or use a thinner sample. Excellent. Cool. So let's test ourselves here. So I am going to try something here. I'll write it down first. So we've got 0.10 millimolar KMnO4. Absorbance is 0.26 at 525. B is 1 centimeter. And find epsilon, the molar absorptivity, and concentration of a solution whose absorbance is equal to 0.52 at 525. Okay. So, come on, you can do it. Ah, oh no. My document camera's not working. Oh, it's black. Oh, come on. Okay. Everything has to fall apart. Okay. So, I have to do this in text here. You guys can see the PowerPoint, right? Of course you can see the PowerPoint, otherwise you'd be yelling at me for a while. So, so what do we calculate here first? Concentration or epsilon?
I want to say epsilon. That'll be the same for both parts because it's the same analyte.
Okay. So someone other than Cindy, tell me, is epsilon an intensive or an extensive property?
Is intensive inherent to the object?
Yes.
Think intensive.
Yes. Yes, exactly right. So for example, if I take, if I go to Mars and I synthesize some potassium permanganate, and I measure the extinction coefficient, will that be the same as the extinction coefficient that Kareem measures for permanganate on Earth? Van, do you know the answer to that?
I think it's the same.
Excellent. Excellent. That's an intensive property. I just wanted to see if you were awake. Or if the sea anemones, what are the jellyfish had eaten you. I wanted to make sure the jellyfish didn't eat you.
Okay.
Good. Good. I'm glad the jellyfish didn't eat you. Okay. So first we calculate epsilon, right? And so E is equal to A over BC, right? Equals 0.26 over 1.000 times 0.00, oops, times 0.00010 molar. Right, so that's 10 to the minus 4 molar. So 0.26 times 10 to the 4 is 2.6 times 10 to the 3 is equal to 2600. M minus 1, Cm minus 1, right? Now C will equal A over B epsilon. Right? Then we just have to substitute the absorption in 0.52. Oh my God. What's the relationship between 0.26 and 0.52? Factor of 2, right? So what is the concentration of this new guy going to be? 0.20 millimolar. I didn't have to do the calculation, right? Because 0.1 gave an absorbance of 0.26, and what gives an absorbance of 0.52, right? 0.52 is twice of 0.26. Therefore, the new concentration is 0.2. Yeah.
I like how excited you got when you found out it was double.
I know, I'm such a dork. I'm such a dork. But I wear it proudly. Where's my dork thing? Hold on, I'll get it. I need a filter. Where's the dork setting? There we go. There's my dork setting.
Is that a pizza or is that a hat?
How did you do that?
It's a pizza hat. It's literally a pizza hat. And I do it using magic, Fook. It's magic. So I actually asked the question of my Chem 250 course last fall. I said, when will it be possible in real time to substitute yourself for President Obama in a video, right? So when can I, instead of being me, when can I just be Obama in a video in real time? And I don't think it's possible yet, but we're getting there. And I'm going to say 10 years. So that will be 2030, and I'll probably be dead, but who cares? Actually, who knows? I might not be dead. Just I have a bad heart, so I could be dead. Yay! Cheers.
No, not cheers. Not cheers.
I disagree. I've talked to you. You have a good heart.
Oh, thank you, thank you, thank you. Well, you know, the jury is still out on that, shall we say? But let's see here. So okay, here's the stupid transferrin thing. We've already done this problem in the homework, right? We did a transferrin problem. Oh, right. So you reduce the iron 3 and it's released from the protein. This is thioctic acid. Oh my God, that's wild. It forms a disulfide. That is so weird. Why would it do that?
You are the one who made these slides, right?
No.
Okay.
I didn't. I have.
So you're looking at this like you've never seen it before.
I confess I haven't seen this one before. No. I didn't make these slides. I have a whole set of slides, and they're actually on the website. You can look at them if you want.
Yeah.
But it's just when it changed to online, I'd been worried about taking people into weird places with the class for a long time. Can you imagine that? Me being worried about taking you guys into weird places?
Weird by your standards?
Well, no, weird by the world standards, you know? And so I decided, no, I'm just going to go with a canned course. And I know Dan Harris, like the guy who did this course, right? And he's a real smart guy, and I really trust him to know, like, kind of like have the pulse, you know, of analytical chem. So I said, no, I'm just going to go with your stuff, right? But it's just this is interesting to me, right? That you can take this thiol group here, right? This is just this is acetic acid with a thiol on the I think this is probably the 1 carbon here, basically, um, and then what happens is it loses that hydrogen, and then it forms a disulfide, right? And this has got to be a multi-step reaction here, but it reduces, it's a good reducing agent here if it'll reduce that iron 3, right? So anyway, so you reduce it with a thioctic acid there, and then you add trichloroacetic acid, precipitate the proteins, leave iron 2, centrifuge it down. When you centrifuge, you remove the protein precipitate, but not the iron 2, or the iron 3 rather. No, the iron 2, sorry. And then you, to measure the iron 2, you add ferrazine. And ferrazine is this weird bipyridal type molecule. And there you got it. You've got the iron ferrazine, and it absorbs strongly at around 580 or 590, right? 562, whatever, right? And then you can also measure copper that way, but you can reduce the copper interference with thiourea or something like that. And the masking here, this is what we're doing with the copper is we're masking it, right? Oops. And to mask an interferent is to complex it so that it doesn't absorb in the same region where your sample does, right? So that's an important concept here. So masking, that'll come up later, like on an exam or something. So you warm up your light source, you process your protein with all of these things, right? Then use a mill of DI water as your blank. Then you calibrate your spectrometer using iron 2, right? And then by doing that, you get a calibration curve. And then you simply place the absorbance of your protein onto this line. And in this case, whenever you do a calibration like this, right, the nearer your measurement is to the origin here, the more important it is to include any small offset that you get. Wait, strike that, rewind. I'm not going to say that. In this case, we're out here, and we're going to include the 0.015, no explanation. I don't know why I said that. Okay. Now, the amount of iron is A minus B over M, right? So the transfer function is A equals MC plus B. And if you invert that, C equals A minus B over M. You gotta group these guys. So there's A minus B divided by M there. So that's basically how you do that. And so we can so this is in micrograms per milliliter, right? So if we got an absorbance of 0.2, then the way we would do this is we would just say C equals A minus B over M equals 0.200 minus 0.015 over 0.0670. Oops, darn it, I suck. 0.0015 over 0.067. Right, 0.067. Yeah. Oops. And this is going to be equal to 2.96. 2.96. Oops. All right. And this is going to be micrograms per ml. And C in molar units. Divide by the molar mass, 55.85, and multiply by 1,000. And that's going to be moles per liter. That's a large value. No, this is 10 to the minus 6. This is 5.30 times 10 to the minus 5 molar. Okay. So, now, okay, so here's a little piece of, I'll just finish with this one here. And this is a little unit on preparing standard solutions. And I'm going to get a new I'm going to use a different filter here. So, okay. So what we did here was we made a 1,086 part per million iron stock standard. So what this means here is that we took this many grams of iron per liter, right? We took 1.086 grams of pure iron wire, right? We dissolved it, but then we diluted it to 1 liter, right? And so this is 1,086 milligrams per liter. Or also 1,080 or 1.086 micrograms per milliliter. So this is 1.086 milligrams per liter equals 1.086 micrograms per milliliter. And so this is the same unit here. Milligrams per liters and micrograms per mil. These are all parts per million. Right? And so the question is, how do we go from 1,086 down to 2, 3, 4, 5, 6, down to these low values here? And the answer to that is we have to dilute them by a factor of 1,000, right? So the way to do that is to take however many mils and dilute them to a liter, right? That's one way of doing this. So let's just take a look here. So this is one way to do it. This is actually going to create 1 liter of 3 parts per million, 3.258, 1 liter of 4.344, etc. So this will create an entire liter of these new concentrations. And in addition, this is going to create, or this is going to consume and create 1, 2, 3, 4, 5 liters of 10th molar hydrochloric acid, right? So this is literally like crazy amounts of waste to generate for this type of experiment. And I don't know, I would be tempted to fire you if you did this for me. If I had a commercial analysis lab, and I said, oh, prepare standards at, between 3 and 9 parts per million, and you did it this way, I would be pretty irritated, because this creates a huge amount of waste. So, Nicholas, how could we do this without creating such a goddamn horrific fuck ton of waste? Oops. I used a bad word. I got to put my hat back on. Sorry.
More extra credit points in the swear jar.
Oh, that's right. That's right. I need to put a, oh gosh, there's 11 chats. Come on, stop asking about that stuff. Okay. All right. So, Nicholas, are you there?
Hello.
Hello. How can you
Could-
do this? How can you do this without creating so much waste?
Probably could have started with a more dilute sample than like 1,000 parts per million,
Okay.
and then you could use smaller volumes.
Well, which one?
What do you mean?
You can do them both? You can do
I'm
both of them?
saying, like, didn't you start with like 1,000 parts per million as your stock solution? Couldn't you make something more dilute than that to make it so you don't have to use as much
Mm-hmm.
in the end?
Yeah, you could use a more, you could use less iron, right? And you could start with that, and then you could make 100 instead of 1,000 part per million stock standard. You can make 108.6, right? So, can you measure 0.1086 grams on our balances here? They're Mettler balances. And the answer is yes, you can. The last digit's a little bit shaky, but you can totally do that. So that is one way. Whom should I pick on to get the other option, right? Let's say we have 1,086 parts per million, and we want to dilute it down here. What's another option? So this is, we take 3 mils, dilute to 1 liter. And you're going to be fired if you create 5 liters of 0.1 molar hydrochloric acid. So how else can you do this? Cindy?
I don't know. I was thinking of if we could try to dilute it, but we've already done that.
Yeah. So if you're basically, it's actually really common to buy a stock standard, and they almost always come as 1,000 parts per million, plus or minus, a little bit. So if we have 1,086 part per million stock standard, how can we create less of
Can we start with, let's say, 1 milliliter of stock solution diluted, and then take our diluted thing and, maybe a portion of that and dilute it a little bit more?
Yes. Yeah, absolutely. So we can do a serial dilution. All right. go from 1086 down to 108.6 parts per million. That's a good way. But then then how would we get to say 3 from there and not make a liter of final solution, right? Because it all has to be 0.1 molar HCl. And that's really where the problem is. We're just creating so much HCl waste. Okay.
Can you do an adversarial dilution and then use that to make those samples?
So you go down from 108 to 10.8, right?
Yeah. Oh, 10.86, right? Yeah, you can do this, you know. Then how do you go from 10.86 to 3, right? Then you have 3 mil. What will you do? What physically will you do? You need two new volumes, right? You need a V1 and a V2, right? Because, you know, what we're doing here is we're exercising our muscles on C1 V1 equals C2 V2, right? So I'm going to leave it here because we have to stop. But this point here, this is one point where I need you guys to be able to just blow past every time you see it. And there's very simple solutions to this, but I want you to come to them on your own, so you never ever forget them. Okay, so I will answer the chat questions offline if that's okay. All righty. So I will, I'm sorry I didn't look at the chat earlier, so I missed a few questions. Okay, everybody, I've got to get ready for lab now, and I will see everybody else tomorrow and Wednesday.
Thank you. See you later.
Thank you. Thank you so much.
See you later.
Bye.
Taro.
Bye, Fook. Bye.
Dr. T,
Yes.
real quick, is there anything that we need to read or look up before we come to lab?
I should have given you something, but no. Just come. I'll explain everything we need to know.
Okay.
Sounds good. Excellent.
All right, I'll see you next class.
Bye-bye.
Dr. Taro, is it possible for me to change to tomorrow just for this week? Or I'm in the Wednesday cohort?
I'm not sure. I have to look at the schedule. I'll take it offline, okay?
Yes, sir.
Okay.
Thank you.
Bye-bye. Sure.
Yes, sir.
No problem.